Hello everyone. In this video, we will continue to examine topic 4.4, wave behavior, and in particular, we will begin to examine the phenomenon of diffraction. So, the basic phenomenon of diffraction, which we'll end up speaking a lot about, so this will just be a short introduction, but the basic phenomenon of diffraction is the spreading out of waves as they go past an obstacle or through an aperture. And the aperture is our technical word for an opening. So, if you take a look at this diagram right here, you can get a sense of what is going on. If plane waves or planar waves come in here and they reach a boundary that has a small gap in it, a small opening, you can see that the waves, when they hit that small gap or small opening, will actually spread out here. And this is fundamentally pretty important. This is how, for example, if you are standing outside the physics classroom, I can hear you loud and clear because those waves diffract around that particular boundary. We see diffraction with water waves and with light as well, as we'll see a little bit later on. You can see that as that opening increases, part of the wave that is sort of in the center here continues on as sort of a planar wave, but it is still sort of bending around the corner here. The effect decreases as the size of that opening gets bigger, but you still get bending at the edges. That is known as diffraction. You get the maximum diffractive effect, for reasons we'll explain later, when the wavelength of the wave is about equal to the aperture size. So notice that you do not see diffraction, for example, when light goes through a doorway. If light goes through a doorway or a window, you'll see a nice window-shaped outline behind it. Okay, so if light passes through a window, you'll just see the outline of the window behind it because the wavelength of that light is so much smaller than the opening. If you take this diagram and increase that opening 1,000-fold, that's the basic equivalent. So, what properties remain the same or change? Well, of note, the frequency, the wavelength, and the velocity of the wave all remain the same in the phenomenon of diffraction. However, the amplitude, energy, power, and intensity all decrease as the waves spread out. So, due to the conservation of energy, if that wave is spreading out, then that energy will be transferred to a larger area, and therefore the amplitude, energy, power, and intensity of the waves decreases. And you can see that by noting that, if you were to draw some rays on these wavefronts with plane waves, those rays stay at the same position relative to one another, whereas if that wave is spreading out, those rays diverge. And because the rays diverge, the amplitude, energy, power, and intensity of the wave decreases. It is most important for you to know that the effects of this phenomenon, known as diffraction, are most significant when the size of the obstacle or aperture is roughly the size of the wavelength. Um, this is really crucial for you to be able to know, and it is an approximate thing. They don't have to be exactly the same size, but they need to be in the same ballpark to get this effect. One more comment. I am very sorry that all these words sound the same. So reflection, refraction, and diffraction are all different wave phenomena, and unfortunately you need to know all the terms and to be able to keep them straight. The one extra thing to note is that not only does diffraction occur as waves enter a particular opening or aperture, but we also call the phenomenon of those waves bending around obstacles. So that could be seen as like one end of the aperture, and also sort of individual obstacles here, like so. That is also diffraction. So we consider diffraction to just be this bending around the obstacle and behind it, um, as you've seen here. And one more comment, one more sort of practical application of this. This is part of why you can receive radio, for example, if you are standing behind your house relative to the antenna. So those radio waves pretty easily diffract around the obstacle of your house. But if you go behind a mountain, it is far less clear that you will not be in the shadow. And you can kind of see that in that visualization here. You can imagine something standing right here may not receive significant amplitude from the waves, whereas something standing right here certainly will.